Welcome to AI Explained, a podcast where we break down the complex world of artificial intelligence into digestible, fascinating discussions. I'm Clara Chen, an AI researcher with a background in computational linguistics.
And I'm Leo Martinez, former software engineer turned tech ethicist. We're excited to take you on this journey through the evolving landscape of AI technology.
Across this series, we'll explore everything from the basic building blocks of AI to cutting-edge applications and the ethical questions that keep us up at night.
And trust me, some of these questions really do keep Clara up at night. I got a text from her at 3 a.m. last week about GANs and digital forgery. It was Vans and digital forgery. It was intense.
Hey, I apologize for that, but you have to admit it was an interesting paper. Anyway, today we're starting with the foundations, how AI began, what it actually is, and how we got to where we are today.
Episode 1, The Foundations of AI, from early dreams to modern reality. Let's dive in.
So before we get into the history and development of AI, we should probably define what we're actually talking about. What is artificial intelligence?
Well, that's surprisingly controversial. I mean, the term intelligence itself is hard enough to define for humans, let alone machines.
Right. In the broadest sense, AI refers to machines or systems that can perform tasks that typically require human intelligence, things like visual perception, speech recognition, decision-making, and language translation.
But what about creativity? My daughter's third grade class used an AI art generator last week, and she came home absolutely convinced the computer was thinking like an artist. But was it really?
That's where we get into distinctions like narrow versus general AI. What your daughter used was definitely narrow AI, also called weak AI, which is designed to perform a specific task. It's not actually thinking the way humans do.
But what about general AI or strong AI? Is that the sci-fi version where machines become conscious?
Essentially, general AI would theoretically have the ability to understand, learn, and apply knowledge across different domains, similar to human intelligence. But despite what movies suggest, we're nowhere near achieving that.
But how would we even know if we did? This brings us to the Turing test, right?
Exactly. Alan Turing proposed this in 1950 as a way to determine if a machine can exhibit intelligent behavior indistinguishable from a human. Basically, if a human evaluator can't reliably tell the difference between responses from a machine and a human, the machine passes the test.
But wait, with today's large language models, couldn't you argue some systems are getting close to passing? I spent 20 minutes chatting with an AI assistant last week about my weekend plans and completely forgot it wasn't human.
That's the fascinating thing. The Turing test has limitations. A system might sound human in conversation, but lack true understanding or consciousness. That's why researchers have proposed alternative frameworks like the Winograd Schema Challenge or machine consciousness tests.
So basically, we're still figuring out how to measure machine intelligence, even as the machines get smarter. No wonder my coffee went cold this morning while I was debating with my smart speaker about the weather forecast.
Let's talk about how we got here. The history of AI is fascinating and honestly, not as recent as many people think.
Right, it didn't just start with ChatGPT in 2022.
Not even close. The conceptual foundations go back to the 1950s, with the Dartmouth Workshop in 1956, often cited as the official birth of AI as a field. John McCarthy, who coined the term artificial intelligence, organized it along with Marvin Minsky, Claude Shannon, and others.
But people were dreaming about intelligent machines way before that, right? I remember reading about automata from centuries ago.
Absolutely. The idea of creating artificial beings appears in ancient myths across cultures, but the mathematical groundwork for modern AI came from people like Alan Turing in the 1930s and 40s, and earlier logicians like George Boole and Gottlob Frege.
So we had these big dreams in the 50s and 60s. What happened next? Because I'm pretty sure we didn't have Roombas and voice assistants by 1970.
No, we didn't. In fact, the field went through what we call AI winters periods of reduced funding and interest when progress slowed down.
Wait, there was more than one winter? I thought it was just that one big disappointment in the 80s.
There were actually several cooling periods. The first major one was in the 1970s, after initial optimism about machine translation and other applications proved overhyped. Then another hit in the late 80s and early 90s when expert systems didn't deliver as promised.
But why? Were researchers just too optimistic?
Partly, but they also underestimated the computational requirements and the complexity of the problems. Early AI researchers thought intelligence could be recreated through logical rules and symbol manipulation alone.
I remember my first programming class in college. I thought I'd build an intelligent chatbot in a weekend. Spoiler alert, I did not. I barely managed to make it respond to keywords.
Classic rookie mistake. But even the experts were learning as they went. The real revival came with breakthroughs in machine learning, especially when neural networks made a comeback in the 2000s and 2010s. Suddenly, approaches that had been abandoned decades earlier became viable with more data and computing power.
So basically, the early AI pioneers had the right ideas, just the wrong decade?
In many cases, yes, though there was also a fundamental shift from trying to program intelligence explicitly to creating systems that could learn from data.
Let's talk about those different approaches. I remember when AI mostly meant if-then rules and decision trees.
That's right. Those rule-based systems were dominant for decades. Researchers would program explicit knowledge and logical operations, essentially trying to codify human expertise.
But that didn't scale well, did it? I mean, imagine trying to create rules for every possible scenario in something like driving a car or recognizing objects.
Exactly. The knowledge engineering approach hit walls pretty quickly. You'd need infinite rules for infinite situations. That's where statistical methods started gaining traction using probability and data patterns rather than explicit rules.
But what about that fundamental shift you mentioned from programming intelligence to creating learning systems?
That's the data-driven revolution that's dominated the past decade. Instead of telling machines exactly how to solve problems, we give them tons of examples and let them figure out the patterns themselves.
But surely the massive computational advances were just as important. I mean, my smartwatch today has more processing power than the computers that sent astronauts to the moon.
Computational power has been absolutely crucial. Neural networks were theorized decades ago, but they were computationally infeasible until recently. The combination of big data, powerful GPUs, and algorithmic improvements created the perfect storm for AI advancement.
I'm still amazed by how much of this runs on graphics cards originally designed for video games. My teenager's gaming setup is basically an AI research lab.
It is pretty ironic. GPUs turned out to be perfect for the parallel processing needed in neural networks. That's a great example of how advances in one field can unexpectedly accelerate another.
But wait, not all modern AI uses neural networks, right? Aren't there still hybrid approaches?
Absolutely. While deep learning has dominated headlines, many practical AI systems still incorporate rule-based components alongside statistical methods. The most effective solutions often combine multiple techniques. So now that we've covered the evolution of approaches, let's break down the different types of AI systems that exist today.
I'm guessing this is where we clarify that my phone's voice assistant isn't actually plotting to take over the world.
Exactly. Let's start with reactive machines, which are the simplest form. These systems respond to inputs without any memory of past interactions or ability to learn from them. IBM's Deep Blue chess computer is a classic example, incredibly sophisticated at chess, but with no concept of past games.
But most modern AI systems remember things, right? My smart home definitely knows my routines.
That's limited memory AI, which can use past experiences to inform future decisions. Self-driving cars use this type. They observe other vehicles' speed and direction to make predictions and navigate safely.
But what about the sci-fi stuff? The robots that understand human emotions and have self-awareness?
Those fall into two theoretical categories we haven't achieved yet. Theory of mind, AI, which would understand that humans have thoughts and emotions influencing their behavior, and self-aware AI, which would have consciousness and understand its own existence.
But some chatbots seem to understand emotions. My niece had a heartfelt conversation with an AI companion last month when she was feeling lonely at college.
What your niece experienced was a sophisticated simulation of emotional understanding, not actual empathy. The AI recognized patterns in her language that indicated certain emotions and responded with predetermined types of supportive messages.
But if it walks like a duck and quacks like a duck, does it matter if it's not actually a duck, if it's helping her?
That's a profound question that philosophers and ethicists are actively debating. For practical purposes, the appearance of understanding can be valuable, but it's also important to be clear about capabilities and limitations.
Fair point. So where do hybrid systems fit into these categories?
Hybrids typically combine approaches from different AI paradigms. For instance, many modern applications use neural networks for perception tasks like image recognition, but symbolic reasoning for logical decision-making, getting the best of both worlds.
So where exactly are we now with AI in 2025? And I feel like every day I see headlines about some new breakthrough, but then my smart speaker still can't understand when I ask it to play that song from the movie with the guy and the thing.
That's the paradox of current AI, simultaneously impressive and frustrating. Today's systems can diagnose certain medical conditions better than doctors, generate remarkably human-like text, and beat world champions at complex games, but they still make basic errors that any human would avoid.
I experienced that last week. An AI image generator gave a person 6 fingers in an otherwise photorealistic image. My 5-year-old nephew noticed immediately and couldn't stop laughing.
Classic example, current AI excels at pattern recognition within domains it's been extensively trained on, but lacks common sense reasoning and a true understanding of the world.
But news outlets often make it sound like AI systems are nearly human level or beyond. Isn't that misleading?
Absolutely. There's a tendency to anthropomorphize AI systems, attributing human-like understanding and intentions to them. A language model generating coherent text doesn't understand what it's saying any more than a calculator understands mathematics.
But what about those stories of AI systems doing unexpected things? Doesn't that suggest some kind of independent thinking?
Usually not. Those unexpected behaviors typically stem from patterns in training data or optimization processes, finding unanticipated solutions, not from the system developing its own goals or consciousness.
Speaking of data, it seems like that's the real secret sauce behind recent AI advances, not just clever algorithms.
100%. The data revolution has been fundamental. Today's models are trained on unprecedented amounts of information, billions of documents, images, and recordings. They're essentially sophisticated pattern matching systems operating at massive scale.
Which explains why AI is suddenly everywhere in 2025. We hit critical mass with data availability, computing power, and algorithmic improvements all at once.
Right. And now we're seeing AI capabilities being embedded into virtually every software application and digital service. The technology has moved from specialist research labs to mainstream consumer products in just a few years.
Though I still can't get my parents to trust their AI-powered tax software. My dad insists on printing everything out and checking the math by hand.
Given some of the hallucination problems with early models, maybe your dad's caution isn't entirely unwarranted. Trust and reliability remain significant challenges as these systems become more prevalent in our daily lives. Well, we've covered a lot of ground today in our inaugural episode of AI Explained. We talked about what AI actually is, traced its evolution from theoretical beginnings to today's applications, and explored the different types of systems that exist.
And importantly, we clarified what current AI can and cannot do. I think understanding those limitations is crucial as these technologies become more embedded in our daily lives.
Absolutely. The gap between public perception and technical reality in AI is probably wider than in any other technology field. Part of our mission with this podcast is to help bridge that gap.
And speaking of bridging gaps, next episode we'll be diving into machine learning, the technology that's powering most of the AI applications people interact with today.
That's right. Episode 2 will explore how machines learn from data rather than explicit programming, the different approaches to machine learning, and why this paradigm shift has been so revolutionary.
We'll break down supervised learning, unsupervised learning, and reinforcement learning concepts that sound technical but are actually pretty intuitive once you understand the basics.
And we'll discuss the critical role of data quality and the challenges of bias in training data. I'm particularly excited to share some recent research on how these issues are being addressed.
Is this where I get to bring up that disastrous machine learning project from my last job? The one where our customer recommendation system started suggesting winter coats to customers in Miami during summer?
I was wondering when you'd mention that. Yes, real-world examples, both successes and failures, will definitely be part of the discussion.
Perfect. So join us next time for Machine Learning, the Engine of Modern AI. Until then, I'm Leo Martinez.
And I'm Clara Chen. This has been AI Explained. Thanks for listening. And remember, artificial intelligence might be complex, but understanding it doesn't have to be.
Thanks for spending this time with us. Don't forget to like, subscribe, and of course, share this podcast with friends who want to improve their English. Leave your thoughts and questions in the comments. We always appreciate your feedback. See you in the next episode.